Hey everybody, this will be the tutorial video for section 10.1 on the Pythagorean theorem. A little bit of geometry applications today. We get to look at triangles. All right, I'm going to present my screen. You should have the 10.1 handout in front of you. And here it is. So today's goal is going to be able to learn about what's called the Pythagorean theorem, which is probably, I call it like the celebrity of theorems in geometry class. So you'll talk a lot more about this next year, but reason we're doing it in chapter 10 here in algebra is because it actually combines a couple different ideas that we've talked about, and that's solving quadratics as well as simplifying radicals. One thing I also, one second. Sorry, give me one sec. Okay. Yeah, so it uses two big ideas that we talked about. One from chapter 9, which was solving quadratics, and another idea that it uses from chapter 10, and this is the reason why I did section 10.2 first, is it also allows us to use these properties of square roots and radicals that we've been talking about. So that's the reason I flip-flop section 10.2 and 10.1. Okay, so we're going to look at the Pythagorean theorem, and we're going to talk about what's called its converse. So that's another term that we're going to define later. And then we're going to end with some real-world applications, some word problems to tie this all together. Before we actually get into what the Pythagorean theorem is, first of all, let's talk about some vocab. What's a theorem? A theorem is just a statement that can be proven true. Okay, you can use a chain of reasoning, you can use an argument in order to justify why it works. Honestly, if you ever think about the occupation of being a lawyer, lawyers are trying to justify their arguments step by step when they go into the courtroom. Think of it as a real-world theorem. That's really what lawyers are trying to do when they go in the courtroom. It uses logic and reasoning to arrive at a conclusion. So before we get into Pythagorean theorem, you'll see I have this object right here, which is what we call a right triangle. A right triangle is a triangle that has a right angle. And you'll know it's a right triangle because you'll see that little box in the corner. That little box in the corner is the right angle. And that just means it has 90 degrees. Again, you'll do a lot more of this in geometry next year, but, gives us a start. The different pieces of the right triangle, the side that's across from the right angle, so I'm going to highlight it in blue. This long side right here, it's actually the longest side of the triangle. This is what we call the hypotenuse. So make sure that you watch your spelling on that. Hypotenuse. Okay. That's always going to be the side across from the right angle. So what I always do is I locate the right angle, I draw an arrow across from it, and then boom, I got my hypotenuse. The other two sides that share the right angle are what we call the legs of the right triangle. So put the blanks down here. The hypotenuse is the side across from the right angle, and the legs are the other two sides of the right triangle that share the right angle. This right here, maybe a little throwback to childhood, that is Phineas from Phineas and Ferb. Maybe you never noticed, but his head is in the shape of a right triangle. Lots of these animated shows use some pretty cool geometric figures for their cartoon work. So Phineas and Ferb, little right triangle there. So what does the Pythagorean theorem say? I have a right triangle down here, and you'll notice that I have the legs labeled A and B, and I have the hypotenuse labeled C. Pretty typical setup when we do right triangles. We like to use the letters A, B, and C. What the Pythagorean theorem says is that if a triangle is a right triangle, so first and foremost, this only works if you have a right triangle, the sum of the squares of the legs, A and B. So let's break that down. Sum of squares. Sum means addition. So what does that mean? That means I'm adding something together, but I'm not just adding the legs, I'm adding the squares of the legs. So you'll notice I have a squared plus b squared equals the square, again, that means I'm going to be raising it to an exponent of 2, of the length of the hypotenuse c. So I'm not using c, I'm using c squared. So Pythagorean theorem really just says if I take this leg and square it, I take this leg and square it, if I add those two values together, I'm going to get the length of the hypotenuse squared. And again, it's real important that you make sure that you're making these squared. The Pythagorean theorem does not say that a plus b equals c. Put a big box around that and then put a big slash through it and put no. No! Think back to that video I showed you earlier in the year of The Office. I cry every time this happens. And convince yourself, why wouldn't that work? Let's just say you do this with the numbers 3, 4, and 5. Okay, you can check this. 3 squared plus 4 squared does equal 5 squared. Okay, 9 plus 16. 5 squared is 25. 9 plus 16 is 25. 25 equals 25. Well, that works. But then let's just say that you were thinking, well, what if I just get rid of these little squares? Would it still work? Does 3 plus 4 equal 5? No. 7 does not equal 5. Huh? Not true. Okay? So it only works if you square them. It's also very important that you make sure that c is the length of the hypotenuse. That's always going to be the one that's on the side by itself in that equation. So the side that's represented by c is always going to be the hypotenuse. And I mentioned this a little bit earlier, but the hypotenuse is always the longest side. And the reason for that is because it's across from the biggest angle, which is 90 degrees. Okay. You'll learn next year all the angles in the triangle have to add up to 180 degrees. If you already got 90 degrees used up in the corner, these angles right here can't be more than 90 degrees. They can only be less than 90 degrees. Okay. First thing you should always do with the Pythagorean theorem problem is you should label which sides are your legs and which side is your hypotenuse. That's going to be real helpful when you're setting up the equation. So let's look at how this works. In the first one, okay, first part, we want to find the length of the missing side of each right triangle. Whether they give you a description or they draw a picture depends on the problem. In example 1, they don't give us a picture, so I always like to draw a picture if I don't have one. A and B, remember, are your legs. They want you to find C, which is your hypotenuse. So I'm going to make my legs 6 and 8. My hypotenuse is across from the right angle. There's C. So leg, leg, hypotenuse, I like to label. And I'm going to set up my theorem. My theorem said a squared plus b squared is equal to c squared. That's the Pythagorean theorem. Discovered a long, long time ago by a guy named Pythagoras. And actually, there's a lot of debate. He actually wasn't the first person to discover it, but for some reason, he gets the credit, which isn't super fair, but that happens sometimes. So if I set this up, leg squared, one of my legs is 6. So 6 squared plus my other leg is 8. Make sure we square it, equals the length of the hypotenuse squared, which we're calling C. So there's my equation. And now we don't want to get rid of the 2's. We're going to keep those for now. 6 squared, I'm going to simplify. That's 36. 8 squared is 64. Add them together. And then on this side, I have c squared. So I get 100 equals c squared. And now you can see how this is a little bit of a throwback to chapter 9. This is a quadratic equation. I can square root both sides to solve that. Technically, I would get 2 answers. I would get 10 and I would get negative 10. Remember, we always get plus or minus. But this is a geometry problem. If you were to say that c was negative 10, you'd be saying that the length of this hypotenuse is negative 10 units long. Length can't be negative. So a lot of times in these geometry problems, we're not going to use the negative numbers. Okay? Length must be positive. That's the reason why I'm crossing that answer out. So throughout the rest of the section, I'm going to ignore the negative answer. I'm not even going to write it. But if it's not a geometry problem, make sure you're still using the plus or minus when you square root both sides. Number 2, I'm going to label. First thing I do is I locate my right angle. I draw an arrow across from it, and boom, I know that 13 is my hypotenuse. So that means this is a leg, and this is a leg. Leg squared plus other leg squared, which they're calling x, equals hypotenuse squared. So a little different than number 1. This time they actually gave us the length of the hypotenuse, and we're solving for a leg. So I'm going to simplify. 12 squared is 144, plus x squared equals 13 squared is 169. And I'm going to solve this like a quadratic. I'm going to subtract 144 from both sides. I get x squared equals 25. Square root both sides. Again, it would normally be plus or minus 5, but since it's side lengths, I'm only going to use positive 5. I'm not going to use negative 5. So those are my first two. Hey, why don't you give one a shot? Take a look at the you try problem that I have listed here. First thing I want you to do, before you even set up an equation, I want you to label what are your two legs and what's your hypotenuse. So take about 5-6 seconds, just label L, L, and H. Okay, so you should have gotten that the bottom side is the hypotenuse in this one, since that's across from the right angle. There's your leg. There's your leg. Okay. Now I want you to try to set up the equation before I write it out. So give it a shot. See if you can set up what the equation would be. We don't know this side. Let's call it x. So you should get 15 squared plus 8 squared equals x squared. And if you solve that, you would get 225 plus 64 equals x squared. So 289 is x squared. That is on our list of perfect squares. If you're still learning that list and you were to type that in and square root it, square root of 289 is a nice clean 17. So that missing hypotenuse in this problem would be 17. Looking at example 3, notice this time they actually give me a leg. They give me a hypotenuse and I'm solving for a leg. So they're giving me C, I need to solve for B. So if it helps, draw the picture. One of my legs is 2, my hypotenuse is 7, my other leg that's missing is B. Leg, leg, hypotenuse. So 2 squared plus, I'll just leave it as B. B squared equals 7 squared. So I get 4 plus B squared equals 49. Subtract 4 from both sides. And the reason I put this one on here is because, 45 is not a perfect square. You can see where section 10.2 comes into play. When I solve this, I'm going to have to simplify the square root of 45. I don't want to leave my answer as a decimal. I want to use simplified radical form. So think to yourself, what would be the biggest perfect square that you can fit into 45? You should get rad 9 times rad 5. This would be the quickest way of doing it. Rad 9 is 3, rad 5 carries down. So this tells me that B is equal to 3 rad 5. Example 4, first thing I'm going to do, I'm going to label, here's my right angle, across from it must be the hypotenuse. And so I have a leg that's missing, I'm going to call that x, leg, leg. Setting up the Pythagorean theorem here, leg squared plus other leg squared needs to equal hypotenuse squared. So I'm squaring not 58, I'm squaring rad 58. So this takes us back to the last section. I'm going to get x squared plus 49. That side's pretty easy. If you square a radical, remember what happens is square rooting it and then re-squaring it just gives you the number underneath the radical. Because this is just rad 58 times another rad 58. Comes out of the house as just normal 58. And then I solve it. So I subtract 49 from both sides. X squared equals 9. And then remember to square root both sides. So that would mean that that missing leg in this problem would be 3. Take a look at example 5. More x's in this one. Now there's different expressions for the different side lengths. I'm going to label the same thing first. It wants me to find all missing side lengths. So not just solving for x, but I have to find out what 2x is as well. Here's my right angle. I draw a little arrow across from it. There's my hypotenuse, which means this is a leg and this is a leg. So if I set it up, one leg is x, so I'm going to have x squared, plus the other leg is 4 rad 3. Please make sure you don't write it like this, because if you write it like that, you're only squaring the rad 3. This needs to go in parentheses so that the 4 gets squared as well. And on the other side, same thing. If you write this 2x squared, only the x is getting squared. You need the 2 to get squared as well. So you got to make sure that you throw that in parentheses. So make sure you have that before we move on. And now we're going to simplify. Uh-oh. So I get x squared plus 4 squared is 16. Rad 3 squared, remember, is just normal 3. 2 squared would be 4, and x squared would be, obviously, x squared. So x squared plus 48 equals 4x squared. I notice there's only x squared terms. The x term is missing. So I'm going to get my x squareds on one side before I start using square roots. So I get 48 equals 3x squared. Before I square root, I got to get rid of the 3. There we go. So I get x squared equals 16. Square root. And I get x equals 4. So I found this leg's length is 4. But look at the directions. It wants all missing side lengths. I still don't know what 2x is. So I got to plug it back in. So I'm going to substitute. We just found out x was 4. 2 times 4 would be 8. So this missing side length, the hypotenuse, is 8. And this one we already had, so we don't have to solve for that one. So I'm just going to highlight the two final answers. This leg is 4. This hypotenuse is 8. Okay, in example 6, we're going to, again, same directions. We're going to find all missing side lengths. Okay. Now, I have a separate, this example I chose for a reason. It's not the exact same type as the last one. The setup is similar, but the technique to solve it is going to be a little bit different. So take a minute, see if you can set up what the equation would be, and then we'll work on solving it. Take about 10 seconds, see if you can figure out what the equation would look like. So if you label the sides of your triangle, there's your hypotenuse, rad 2x, which means this is a leg and this is a leg. So if I set this up, x squared plus 1 squared, or you could have 1 squared plus x squared, equals rad 2x, that whole quantity is being squared. So that's the equation you should have had. Double check that with what you wrote down. If you need to correct it, correct it. And let's simplify. So x squared plus 1, same trick as last time. The square root and the square are going to cancel each other out. So this is just normal 2x. But you'll notice in this problem, it's a little bit different than the last one. Not only do we have x squareds, we also have an x term, which means square roots is not going to work for this problem. So we either have factoring or we have quadratic formula in our toolbox. Let's try factoring first. Regardless of which method we pick, we're going to have to get 0 on one side. So I'm going to subtract 2x from both sides. X squared minus 2x plus 1 equals 0. If this factors, that means I can find two numbers that multiply to 1, and they're going to have to add up to -2, just using my earmuffs. And that does work. -1 times -1 is 1, and -1 plus another -1 is -2. So this is going to factor into x minus 1 times x minus 1. I can jump right to my shortcut because this lead coefficient is 1. And using zero product property, you'll notice both factors are the same, so I really only have to solve one of these. I'm going to set x minus 1 equal to 0. And if I add 1 to both sides, there's that side length. That's 1. And then I've got to substitute it back in here to rad 2x. So rad 2x, plugging in what we just found, x was 1. The square root of 2 times 1 is just the square root of 2. So this hypotenuse has a length of rad 2. And that answers their question. We found all missing side lengths. This one is 1. This was rad 2. All right, so now we need to talk about what a converse is, because we also want to talk about the converse of the Pythagorean theorem. And a converse really just means we're going to take a statement and flip it around. You'll notice in the original Pythagorean theorem, we wrote it as an if-then statement. We said if a triangle is a right triangle, then the sum of the squares of the lengths of the legs equals the square of the length of the hypotenuse. These if-then statements are going to be real popular next year when you take geometry. These are what we call conditional statements. Just means if-then. Well, if you flip the order of an if-then statement, if you take the part that's next to the if and the then and you reverse them, you get a new statement, which is what we call the converse. I always think of it as like a con man. Like a con man will try to switch something out. Like he might take your wallet and switch it out with something else. Okay, so con, switch, the converse. Just because the original statement is true does not necessarily mean the converse is going to be true. So let's, take the numbers out of it for a minute. Let's just do an example with some words. Makes it a little bit easier to start out. First one says, if Tom is 16 years old, then he is a teenager. Well, that first statement is true. If you have a 16-year-old person, by definition, if you're between 13 and 19 years old, you're a teenager, right? That's true. But let's say I flip these two parts. All I'm going to do is I'm going to take these two parts and I'm just going to switch them. Reverse, reverse. So if Tom is a teenager, I don't want to say he because I want to know who is he. If Tom is a teen, then he is 16 years old. I'm abbreviating a little bit, which is fine. Okay, well, if this is true, that means if you have a teenager, they always have to be 16 years old. Can you find a case of somebody who's a teenager that's not 16? And I can think of that. How about somebody who's 15 or somebody who's 17? They're still a teenager, right? But they're not 16 years old. So this statement is false. For example, think of a 15-year-old. And what I just found here, this is what we call a counterexample. It means I found a specific example that makes this whole statement false. So this goes to show just because the original statement is true doesn't mean the converse has to be true. It could, but it doesn't have to. Here's another one. If you live in Chicago, then you live in Illinois. True statement. Chicago is in Illinois. Flip it around. That would be the converse. If you live in Illinois, then you live in Chicago. Not necessarily. Not everybody who lives in Illinois has to live in the city of Chicago. How about us right now? We're in Libertyville. I'm just going to go Lville. That's not the only example you could use. How about Champaign? Okay, Champaign is in Illinois, but it's not in Chicago. Other towns as well. Naperville. Think of basically any town in Illinois that's not the city of Chicago. It wouldn't be correct, though, to pick an example of a city that's not in Illinois. You still have to be picking an example that's in Illinois. So if I use Los Angeles over here, that would not be a counterexample because that's not even in Illinois to begin with. I need an example that's in Illinois, but it's not Chicago. Okay? Keep the first part true, but make the second part false. Okay. And then a little example. This takes you back to science class. If the temperature is 32 degrees or below, then the lake is frozen. That is the definition of freezing. Freezing point of water is 32 degrees. So if it's 32 or under, it's going to freeze. True. Flip the statement to get the converse. If the lake is frozen, then the temperature is 32 degrees or below. I'm just going to say less than or equal to 32 degrees. Well, lake is frozen. What's the definition of freezing? Freezing is when the water is 32 degrees or below. This is still a true statement. So this gives you a case where both the original statement and the converse are both true. So they don't always have to have the same or different truth value. Sometimes they can match. And again, you'll learn a lot more about this next year in geometry. It might seem strange why we're doing this now. The only reason I'm introducing this is because we want to focus on the converse of the Pythagorean theorem. Pythagorean theorem, remember, if you have a right triangle, then we know a squared plus b squared equals c squared. Well, what if we flip that statement around? If you have a triangle that has three sides, a, b, and c, if a squared plus b squared equals c squared, then it must be a right triangle. That's exactly what I have at the top of the next page. The converse of the Pythagorean theorem says that if you have a triangle with sides a, b, and c, and you know that a squared plus b squared equals c squared, then the triangle must be a right triangle. All we did is we flipped the statement around. When you do this, you need to make sure that c is the biggest side of the triangle. We don't necessarily know if it's a hypotenuse because we don't know if it's a right triangle to begin with. But we do want to make sure that c is the longest side when we check. So how do we check to see if it's a right triangle? They'll give you three side lengths, and you need to verify that a squared plus b squared equals c squared. If you get that equality, that's going to mean it's a right triangle. And if you don't get that equality, that means it's not a right triangle. So for example, if I have a triangle with sides 20, 21, and 29, first thing immediately is I make the biggest side my c value. So I want to see if 20 squared plus 21 squared equals 29 squared. I'm not going to put an equal sign yet. I'm just going to leave a little space because there's a chance it's not equal. But I got to check. 20 squared is 400. 21 squared is 441. So I'm just going to simplify that side. Still leave my blank. 29 squared, I'm not sure what that is off the top of my head. 29 squared is 841. Oh, I want to stop recording yet. Okay, we're still good. Sorry about that. 29 squared I just found on my calculator was 841. And so now I add them up. 400 plus 441 is 841. And the other side is also 841. So now you ask yourself the big question, does 841 equal 841? Yes, it does. It's the same number, which tells me, yes, this is a right triangle because a squared plus b squared did equal c squared. Let's try it with number 2. You have 8, 8, and 8 rad 2. 8 rad 2, you can check if you're not sure, that is a little bit bigger than 8. That's about 11.3. Actually, quite a bit bigger. So there's my c value. So I'm going to plug in a squared plus b squared, leave a little blank. We don't know yet if it's equal or not. Remember, you're squaring this. The whole quantity needs to get squared because I need to square the rad 2, but I also need to square the 8. This one is 64. This one is also 64. I leave a little blank. 8 squared is 64, and rad 2 squared is just normal 2. So this side turns into 128, and 64 times 2 is also 128. So again, I get equality. Because it's an equal sign, that means a squared plus b squared equals c squared. This is a right triangle. If I had gotten not equal to, if these two numbers were different, then it would not be a right triangle. I would be putting no. Try out the 2 on the bottom. I will put the yes or no answer for you. You can pause my video, and then if you want to see the detailed work, check my answer key that I posted in the Google Doc. So pause me, try those out. I will have a yes or no on the screen, and then you can move on to the last page with the word problems. So this one you should have gotten no, and this one you should have gotten yes. If you want to see the detailed work for that, take a look at the answer key that I posted in the Google Doc. I have the work shown for that. All right, last page, just some applications. You can use plenty of applications with the Pythagorean theorem. One really cool one, I actually linked a YouTube video for you that you should have watched before you started this on how Pythagorean theorem is used in the NFL. for players to try to get the optimal distance covered in order to get a touchdown. Pretty cool video. It's only like 3.5, 4 minutes long, and it's got some pretty neat applications of some geometry in there. A baseball diamond is another good example. Distance you need to run, distance you need to throw. Here we have the length of each side of a baseball diamond is 90 feet. So I got my picture here. They're trying to tell me that all these distances in blue are 90. And that would make sense. We want it to be fair distance between all of the plates, or all of the bases. What is the distance from home plate to second base? So I'm going to locate that in my picture. Here's home plate in pink. Here's second base. I want to know what's the distance from home plate to second base. So I'm just going to outline that in pink. We want to find that length. And anytime you have this like vertical segment and this horizontal segment, those are always perpendicular to each other. So that's a right angle. And so you'll notice what I created here in purple is a little right triangle. So I'm just going to zoom in on that. This is 90. This is 90. And that little pink piece that you see in the original picture, draw it again. That piece right there is my hypotenuse because it's across from the right angle. So I'm going to call it C. Leg, leg, hypotenuse. And we want to find that pink distance. So Pythagorean theorem. We're going to round to the nearest hundredth, which means 2 decimals. 90 squared plus another 90 squared needs to equal the hypotenuse squared. So that's C squared. So this one's 8100 plus another 8100 equals C squared. So that's 16,200. Don't worry about breaking down this radical. You might say, oh my goodness, that's a huge number. We don't want this to be in simplest radical form. We want this to be to the nearest hundredth, 2 decimal places. So I'm just going to type it into my calculator. The square root, so second x squared, of 16200. 2 decimal places, it's 27, but there's a 9 next to it, so you got to round that 7 up to an 8. 127.28. And then you want to put your units on it. They told us we're measuring in feet. So this would be about 127.28 feet. And the reason we're not leaving it in radical form is it would just sound silly to say, oh, the distance from second place or second base to home plate is the square root of 16,200 feet. They're going to say, take a bench. You're not batting today. You sound silly. Okay, second one. Cindy is driving to the mall from her home. She drives 9 miles north and 12 miles east to get there. It says, if there was a road directly connecting the mall to her home, how many miles would she drive? And then we want to also know how many miles would she save herself by taking this route. So I'm going to call this part A. I'm going to call this part B just so we chunk it. Okay, she's driving to the mall from home. So first thing she does, she goes 9 miles north. So you have to know cardinal directions. North means up and east means to the right. West would be to the left and south would be down. So she goes 9 miles north. I'm going to call that 9 miles. Then she turns and goes 12 miles east. Maybe we'll do east in blue. Those are perpendicular to each other, so that makes a right angle. Where's she going, mall to home or home to mall? She's going to the mall from her house. So here's her home, and here's the mall. And how many miles east did she go? 12 miles. So we can see how many miles she drove. She went 9 up. She went 12 to the right. She's driven 21 miles so far. That's a lot of miles to go to the mall. So then they said, though, if there was a road directly connecting the mall to her house. So I'm going to do the same thing I did in the baseball diamond. I'm going to put pink dots. Mall, house. What if we had a direct road that just connected those two together? It would be shorter than 21 miles. So we first want to figure out how long is that distance. Well, that's the hypotenuse of the triangle. So there's C. This is a leg. This is a leg. This is my hypotenuse. So to find that pink distance, I'm just going to do Pythagorean theorem. So that's part A. How many miles would she drive along that pink road? 9 squared plus 12 squared equals C squared. So I get 81 plus 144 equals C squared. 225. equals c squared. And so I get 15 miles. Okay, so to answer part A, Cindy would drive 15 miles. So that's the answer to part A that I labeled. That just tells you how long that new road is. Now we want to know how many miles would she save herself from the original route. Well, the original route was 21 miles. She went 9 up and 12 to the right. And she now only drove 15 along the new road. So if they ever want to figure out how much shorter is it, you just got to subtract the two values. 21 miles minus the new 15 miles would be 6 miles. I'm just going to say 6 miles saved with the new route. So, you know, if she's only going to the mall one time, maybe for one day, maybe not a big deal to go the 21 miles. But if she needs to keep making trips to the mall, maybe it's the holiday time or somebody has a birthday coming up, you know, those 6 miles can add up a lot. That's a whole tank of gas. You could save yourself some money, get something better, like a new math t-shirt, right? All right, last one, little superhero application. Superman flies 2 miles north, then 3 miles east, then 5 miles north again, and then 2 miles east again, and then 5 miles north again. So he keeps going up to the right, up to the right, up to the right. How many miles is Superman from his starting point? Something must keep getting in his way. Why does he keep changing direction? You'll notice there's only 2 directions that are actually brought up in this problem, north and east. So what I'm going to do is I'm just going to color code all the norths in red. North, north, north. And I'm going to color code all the easts in blue. Blue, blue, I think that's it. And so what I can do before I start, you know, I could draw this as is, but it would be kind of confusing looking. He goes 2 north, and then he goes 3 east, and then he goes 5 more north, and then he goes 2 more east, and then he goes, it's like a staircase. He keeps going more and more. And we want to know by the end of his path, how far is he from his starting point? So what's the distance between those pink dots? Well, this is not a right triangle, clearly. But here's what we can do. We can actually make a right triangle out of this by just collecting all the red numbers together and collecting all the blue numbers together. And then we can make our own triangle. Okay. So I'm going to start with the red ones. What's his total north distance? If you add up all of the red ones, 2 plus 5 plus 5, 2 miles, 5 miles, 5 miles. He went 12 miles total upwards, north. And what's his total eastward motion? He went 3 miles to the right and then 2 miles to the right, so 5 miles to the right. And so what I can do, is I can make a nice right triangle with those numbers. He went 12 miles up, and he went 5 miles east. There's my right angle. Now, there's where he started, that's where he ended. Now I have a nice right triangle. I can use Pythagorean theorem. This pink segment I drew is my hypotenuse. It's across from the right angle. There's my leg, there's my leg. So I'm going to set it up. 5 squared plus 12 squared equals c squared. 25 plus 144 equals c squared. 169. And that is on our list. That's 13. So I just found out the problem was asking for how many miles is Superman from his starting point. We just found out now the distance between these pink dots. That's 13 miles from his starting point. So if you see directions that are, you know, the same thing, like if you see a bunch of norths or a bunch of easts, you can collect them together and make your own triangle instead of having the staircase pattern that looks more confusing. And that'll do it for this section. There is a Math Excel posted for you to work on, as well as a review packet for sections 10.1 and 10.2. Okay. Happy mathing.